Assume the three blocks below are of equal mass. The person pulls on cable A in the left direction. One end of cable D is attached rigidly to the earth. Assume the earth does not move in any significant way, and there's no friction between the blocks and the ground. Assume the cables are massless. How would the tensions compare in the cables? We'll create a free body diagram for each of these blocks, showing mainly the horizontal forces. We know that each block is going to have a weight and a normal force, which are equal and opposite. They're going to cancel, so I won't even draw those. What I'm most concerned about is the horizontal forces. So for starters, the person's pulling on cable A, and then cable A is going to in turn pull on the block. So there should be a force directed to the left which shows how this block feels pulled by the cable. Now what else is in contact with that block? Well, cable B is in contact with it. Which way does cable B pull on that first block, though? It's actually going to pull to the right. And we know that the blocks are not going to move in this situation. Assume that the cables don't break and they don't go slack either. So the blocks stay right where they are. Well, the only way this could happen is if the forces were balanced. Now, when cable B pulls on this first block, the block also pulls back on the cable. And when the cable pulls on the second block, the block will pull back on the cable as well. What will happen here is that the same force will appear in all the blocks. Same magnitude distributed throughout them. And so the tensions in the cables will actually all be the same. Now we also know that this part of the earth is going to feel pulled to the left by cable D. So why doesn't this mound of earth accelerate to the left? Well, there are forces within the earth itself that pull back and stop that mound of earth from moving. That's if we treat this little piece as a system. Now let's assume that block D is not rigidly attached to the earth. Person pulls on cable A the same as in the above scenario. What happens? Are the tensions still equal, or would the situation be different? Let's try to analyze this situation with a free body diagram. Cable A pulls on the first block. But we know that the blocks are going to accelerate. How do we know this? There's no friction between the blocks and the ground. So we have to create a free body diagram which is accelerating to the left toward the person. The only way this could happen is if the force pulling from cable B is less than the force pulling from cable A. Okay, now if cable B exerts that magnitude of force on the first block, then it's actually going to exert the same magnitude of force on the other block that it's attached to. But this block also needs to be accelerating. And so the force from cable C cannot be as large as the force from cable B. That same force will be exerted on the second to last block. And the force from cable D has to be even less. Cable D will feel that tiny pull, and it will actually have no other force coming from the right side. And that makes it clear that there's only one unbalanced force on that last block. Now, how big are these tensions actually? Well, if you call this the tension in cable D, then that would match with this one. The tension here would be 2 times what it is on the right. That'll make this a 2 times TD. This one can be 3 times TD. And you see the pattern. The person is actually pulling with 4 times the tension in cable D. So, the tension in A is greater than the tension in B, which is greater than the tension in C, and that's greater than the tension in D. The correct mathematical relationship is this one. The tension in cable C is double the tension in cable D. That's because D is responsible for pulling one of these blocks, but C is responsible for pulling 2 of them. And the more mass we're towing, the larger the force has to be. Now let's look at what happens when a cable is not massless. Let's say it has significant mass. Assume there's no friction and no air resistance. F is the net force acting on this entire system of 2 blocks connected with a cable. To an observer standing on the ground who's not part of this system, would the cable be accelerating or moving with constant velocity? Well, an unbalanced force acting on a system of mass is going to cause an acceleration, and the whole system is going to accelerate. So I'm going to choose choice A. So which statement must be true about the net force acting on the piece of cable containing point B? That's this piece of cable right here. We want to do a free body diagram for it. Would the net force acting on that piece of cable be directed to the left? Would the net force acting on that cable be 0, or would the net force be directed to the right? Well, it has to feel a net force because it has mass. And only a net force can cause acceleration for a mass. So this is the net force. But what are the actual forces acting on that piece of cable? Well, A, the cable is pulling on B from the left side, and it also pulls from the right side. But which side pulls harder? Hopefully we can see from the net force here that the tension at point A has to be greater than the tension at point C. It's the only way that that mass could accelerate. So this tells us something about the distribution of tension in a cable of substantial mass. Since the net force acting on the cable is directed to the left, the tension at point A must be a bit higher than the tension at point C. However, oftentimes a cable's mass is extremely small relative to the mass of the system being analyzed. When that happens, we treat the cable as massless. Let the cable below be a massless cable. For a cable of no mass, how do the tensions at the different points compare? So if you don't have mass, then a net force is not required to achieve acceleration. So the force that pulls us toward A will actually be the same as the force that pulls us towards C. If there's no mass there, then there's no net force required. And we can see that the cable tension would be uniform throughout. So whereas here TA is greater than TC, in this example we see that TA is equal to TC.